Hello there, you're watching Differential Questions by Alexander. Alright, so today we're going to talk about linear differential equations, and I'm putting this extra adjective about first order because our differential equations are only going to have the first derivative. And then I also want to mention that sometimes this topic is called variation of parameter and because of the method. Okay, so instead of giving you the theory, what I'm going to do is I'm going to give you examples and then use the theory to solve the examples. But before we do that, I'm going to review a little bit of Cal 2. And I'm only doing this because we actually are going to use this integral later on in the next problem, in the first actual example. So let's just do review a little bit of Cal 2 and before we actually do the differential equations. All right, so this is a calculus 2 integral, and so the technique here is that we have to use a UV substitution. So UV sub is what you call it. And so here you have to figure out that you have to make u equal to a piece of the difference of the equation, and then dv equal to the other piece, and then you fill in the blanks. All right, so I'm going to choose u to be x, my polynomial, and I'm going to choose dv to be my exponential, ex dx. And that usually is the rule of thumb. You usually make, if you have polynomial multiplied by exponential, you usually make the u equal to the polynomial, and then the dv, you make it equal to the exponential. All right, so the derivative of u is just dx. And now the integral of dv, integrate ex, this is the easy function, so it is just going to be e to the x. All right, so now that you have this information, what we are saying now is that we want to integrate this x e to the x dx, but our uv substitution or integration by parts formula says that this is equal to uv minus the integral of v du. So just a quick review of Cal 2. So now plug in the information that we have. So we have x e to the x minus the integral of e to the x dx. So all I've done is just substitute, and so we just have one more integral to integrate. So this is going to be again e to the x plus a constant c. All right, so that's what the original integral becomes in this case. So a little bit of practice from Cal 2. I hope that is helpful. And now let's start with the actual differential equations topic or example. All right, so again, instead of giving you the theory, I'm going to give you an example here, and the equations given by this is a differential equation, and it's a first order differential equation because the highest derivative is the first derivative. And so in order to solve this differential equation, what we need to do is, I'm giving you the step here, we need to put the ODE into the standard form. And standard form just means that in front of the dy dx, you don't want to have anything. Okay, so you don't actually want to have the x that you have in the equation. And so what do we do? So what we're going to do is we are going to divide by x everywhere. So let me clear this up a little bit to show my steps. So we're going to divide everywhere by x. And when we do that, the equation that we get is, and I'm going to write down y prime just to simplify my life. Actually, I do need to write down the dy dx, and then this is going to be minus 4 over x y is equal to x to the fifth e to the x. Okay. So the first derivative of y minus 4 over x times y is equal to x to the fifth e to the x. All right, so now that you have this standard form, you go into step B. Step B says to multiply this standard form multiplied by the integrating factor. And so let me explain what the integrating factor is. The integrating factor is given by this formula, which I'll put this in purple. So this is the Greek letter mu. So it's the Greek letter m, and it's called mu. So the formula says this is e raised to the integral of the p function x dx. That means you actually have to identify what the p function is. And so the p function is going to be what is in front of the y. So in this case, it's this guy here, which I'm putting a purple circle on it. So negative 4 over x, just to make clear what we're putting here. So we are going to put that function in there. So we have negative integral of 4 over x dx. And so now we have to integrate this. So this becomes e raised to the negative 4 ln of x Let's do a little bit of algebra here, not difficult algebra, but this is the same thing as e raised to the ln of x to the -4. And now the e and the ln cancel out, and then we just get x to the -4. So this means that we have to, okay, so I just explained what the integrating factor is first, okay? So that's part of the theory. So step A was put the equation into the standard form. Step B says we first have to get the integrating factor. So this is what we have in purple. So mu is the purple function, which is x to the -4 power. Now we're going to multiply the standard form equation, which I'll put this in gold. Okay, so this is actually the differential equation in standard form. And now we're supposed to multiply this equation with this purple function, which is the mu. And so when we do that, this is what we get. So let me put this in gray now. So we'll just go up here, and we're going to multiply the differential equation by this x to the -4. So dy dx minus x to the -4 multiplied by 4 over x y is equal to x to the -4 x to the 5th e to the x. It's a little crowded in there, so I'll try to make this a little bit more clear. But all I've done is I took the gold function and I multiply every single term by the purple function that we just got, x to the -4. And so let's just simplify this a little bit, or make it look a little bit nicer. So this is x to the -4 multiplied by dy dx, and then this simplifies to -4 over x to the 5th power after you simplify, and then this becomes x e to the x. All right, so I simplify a little bit, and now here comes the tricky part. So what we have done, we have satisfied part B already. We found the integrating factor, and then we multiplied the standard form equation by that integrating factor. So that's what we have. And now this is the little tricky part. This thing in the red parentheses that I'm writing down, we have to recognize that that thing in the red parentheses is actually the following. This is actually the same thing as the derivative of the mu function that you found multiplied by y. And then this is always going to be the case. On the right side, you just copy and paste. So right side, you just copy and paste. So all we have done is that the thing in the red parentheses, we have to recognize that this is actually equal to the derivative of the mu function multiplied by y. So you can double check, but I'm letting you know that this is what the method is telling us. The method is telling us that when we do this process A and B, at this point, the second to last line, we have to recognize that that thing in the red parentheses is equal to the derivative of two functions when you multiply. All right, so that's one of the tricky parts, and then actually that's the tricky part for the whole problem. Now that we have this, we are now going to integrate with respect to x everywhere. So integrate with respect to x, and then the integral on the left side, the integral and the derivative, they cancel out. And so on the left side, you get the following. On the left side, you get x to the -4 multiplied by y. And then on the right side, you have this integral, which is saying integral of x e to the x. And that is the problem that we practiced right before this. And so the answer to that was x e to the x minus e to the x plus c. So this is where we have to do the uv substitution, but we did that in the previous slide. And so here I'm just giving you the answer. All right, so now what are we looking for? Remember that in a differential equation problem, we're looking for the function y, and so we need to get the y by itself here. And so all we have to do is multiply everywhere by x to the +4. So multiply everywhere by x to the +4. So multiply that by x to the +4, x to the +4, x to the +4, and then x to the +4. So then the final equation that we get is y is equal to, and then this becomes x to the 5th power e to the x minus x to the 4th e to the x plus c x to the 4th. And that's the solution to the differential equation. All right, so that is the method. It's two steps, but then the red parentheses part is where the tricky part comes in. We have to recognize that the red parentheses is equal to the derivative of the product of the two functions, which is the mu function and then the y function. All right, so that's the first example. Now I want to give you another example for the same thing, the same method, but just a different equation and different formulas. Okay, so same type of situation as before. So we have our differential equation, and before we try to solve the problem, we need to put the problem into the standard form. Okay, we have to always put it into the standard form before we can actually write down the integrating factor. So what does that mean? So that means that we have to divide by the x squared minus 9. Remember, we want to not have anything in front of the dy dx. So we divide everywhere by x squared minus 9, divide by x squared minus 9, divide by x squared minus 9. All right, so that is going to give us the following. We get dy dx plus x divided by x squared minus 9. And then there's a y here is equal to 0. Okay, so now that you do have the standard form, and again I'll put this in the black box now. So this is the standard form of the differential equation that was given to us. Now that we have this, we have to identify the p function. So the p function is the function that is going to be in front of the y. So the reason we do that is because we need to calculate the integrating factor. Okay, so the integrating factor formula is the following. So I'll put it here. Let me put it here on the bottom as before. And so this is going to be e raised to the integral of the p dx. Okay, so now this is going to be e raised to the integral of this x divided by x squared minus 9 dx. Okay, so now we have to integrate that integral in purple. And so let me do that to the side here. So let me do that on the very top. The integral of x divided by x squared minus 9 dx. You have to make a u substitution. So u sub. So you are going to make u equal to the denominator. So it's going to be x squared minus 9. And so the du becomes 2x dx. Or I try to rewrite this as 1/2 du is equal to x dx. So I'm going to make this substitution in my integral in the very beginning. So this is my integral in the very beginning. And so when I do the substitution, I get the following. The original integral in gold, in the gold box, this is equal to 1/2 integral of 1 over u du. And so this is going to be 1/2 ln of u plus, technically there's a plus c, but we're just going to write down ln of u. Now we have to resubstitute. So this is going to be 1/2 ln of u, which u was equal to x squared minus 9. Now the 1/2 in front of the ln, we do a little bit of algebra for the ln, and so this is the same thing as ln of square root of x squared minus 9. A little bit of algebra there. And all this to say what? Okay, so we have this thing in the gold box, and then that is the integral that we have in the very beginning. But that integral was the thing that you have on the exponential function. So we have to go back here now. So we're going to go back to the purple line. And so this purple line is going to be e raised to the ln of the square root of x squared minus 9. And so the e and the ln cancel out. So this gives you square root of x squared minus 9. And so what we're saying is this. The square root of x squared minus 9, that is our mu function. And mu is what we call the integrating factor. All right. So do you remember what we have to do once we find the integrating factor? So I wrote down the steps here. And so what we need to do after finding the integrating factor, we need to multiply the standard form. We have to multiply it by the integrating factor. And again, the standard form is given to us in the black box, which I put a gold box now. Okay, so we're going to multiply by the integrating factor. And so this is going to get a little messy here. So let me try to separate things before I start writing down. All right, so this is going to be square root of x squared minus 9, and I'll write this down as y prime plus square root of x squared minus 9, and then there's a x, and then there's a x squared minus 9, and then there's a y. And let me write this in red here at the very end. So this is going to be equal to 0. So separate the two lines like this. So a little crowded in here, I agree. So let me rewrite this a little bit, okay? Actually, you don't have to rewrite anything here, okay? So the thing that I was mentioning in the previous example is that the left side of the equation, the left side will always be equal to the derivative of the mu function multiplied by the y function. On the left side, on the right side, we get a 0 in this case because we had a 0 in our equation. But the method of the integrating factor is you put the equation to the standard form, you get the integrating factor, and then you multiply the entire equation by the integrating factor, and then the left side becomes the derivative of the two functions being multiplied, which are mu times y. Mu multiplied by y. And so let me just write that down here. Just the x, the derivative of the mu, which is the square root of x squared minus 9, multiplied by the y function, and then this is going to be equal to 0. All right, so now that's a simplified version. And so now at this step this is where we have to integrate both sides. So we integrate with respect to x on both sides, integrate with respect to x on both sides. So on the left side, the blue integral and then the red derivative, they cancel out. And so you only get the inside part. So you get x squared minus 9 multiplied by y. And then on the other side, the integral of 0 is just a constant c. The integral of the number 0 is just a constant c. And remember, what are we trying to do here? We're trying to solve for the y function. And so all we have to do is divide both sides by the square root part. Alright, so a lot of handwriting in one box. So I'll try to squeeze all the information here. That way you can see all the details in one single slide. So we found the solution to the differential equation. Remember that the original differential equation was given to you here in the gold box, but we need to put this into the standard form, and so that's why we divide out by the x squared minus 9, and then we got this black box equation. And then this is the same differential equation, but now it is in standard form. Now that we have the standard form, we have to identify the p function. That was the crucial part here. We identify the p function, and that helps us find the integrating factor. All right, so that's two examples here. And now what I want to do is I want to give you one more example. The next example is going to be easier, but I want to include an extra piece of information here. So now this is going to be an initial value problem. That's because we have a differential equation, but we also have an initial condition. Okay? So it's an initial value problem. And so we want to solve this differential equation. So we're looking for the function y that satisfies the differential equation and also satisfies this condition. That if you plug in 0, the output is equal to 4. All right, so let's start with the process. Okay, so what is the first step? Step A says to put the equation into the standard form. It already is in standard form, so we don't even have to do anything here. Okay, we don't have to divide by anything. So it's in standard form. Now that you have the standard form, we want to identify, we want to create or calculate the integrating factor. To do that, we need to identify the p function. So the p function here is going to be the thing in front of the y, which is just the number 1. So once we have that, we create the integrating factor, which is given by this formula, e raised to the integral of p dx. So in this case, this is going to be e raised to the integral of 1 dx, which turns out to be just e to the x. All right, so this one's easy. So now what do we do with this integrating factor? What do we do with this integrating factor? Now that you have found the integrating factor, you need to multiply the standard form multiplied by the integrating factor. Okay, so this one's going to be easier. So let me write it out here. So this is y prime plus y is equal to x. That is our differential equation. And now what we need to do is we need to multiply by the integrating factor. So we're going to multiply by e to the x everywhere. So e to the x, e to the x everywhere. And so when we do that, let me rewrite this just one more time. So this is e to the x y prime plus e to the x y is equal to x e to the x. So when we do this, when we follow step A and step B, we now have to recognize that this thing on the left side, in the red parentheses, this is equal to the derivative of the integrating factor, which is e to the x, multiplied by the function y. It will always be the case. That is the method. Right, and then on the right side, you just copy and paste. Copy and paste the right side. So now that we have this, we want to integrate. So we're going to slap an integral on both sides, and then we integrate. And what do you know about the right side? That right side integral is the integral that we have done twice already. On the left side, the blue integral sign and then the red derivative, they cancel out. And so you just get e to the x multiplied by y is equal to the integral of x e to the x, which is x e to the x minus e to the x plus the constant c. So now what do? Okay. So now we want to get the y by itself, and so all we need to do is we need to multiply by, we can divide by e to the x. That is what we do. But another way to think about it is we multiply by e to the negative x everywhere. So multiply by e to the negative x everywhere. So multiply by e to the negative x everywhere. And I do that because that way I kind of skip one little step, and so I get y is equal to e to the x and e to the negative x. They cancel out, you just get x. And then same thing for the second term, it gives you the number 1, and then plus c e to the negative x. Alright, so this is the solution to the differential equation. But now this problem has an extra piece of information. This problem is an initial value problem, which means that they give you some extra information so that way you can calculate or figure out what the c value is. Alright, so this is telling us that when we plug in 0 into the function, the output is 4. And so that is what we are going to do here. Okay, so let's separate the information here. So plugging 0 into the function, the output should be equal to 4. And so plugging 0 into the function that we just got, is this going to be 0 minus 1 plus c e to the 0 is equal to 4. And so this becomes negative 1 plus c is equal to 4, or c is equal to plus 1 gives you a 5 here. So plus 1, yeah, give you a 5. So that gives you the value for c. So what does that mean? We don't just care about the number c, we care about the function. Okay? We care about the function that satisfies the differential equation and also the initial condition. So that means that we are going to update our function one more time. And so the function that we found is x minus 1 plus 5 e to the negative x. Alright, so this function in gold, this is our solution. X minus 1 plus 5 e to the negative x. Alright, so this is the method dealing with the integrating factor. Some people also call it the variation of parameters, and actually the textbook also mentioned that briefly. So I'm giving you the steps through the examples. I hope that the three examples help explain. Alright, so that's it for this video. I'll see you next time.